Okay, you can see my screen?
Yep.
Brilliant. Okay. All right. So yeah, thank you for having me. And today I'm going to be talking a bit about Armada, which is a project we're working on at G Research. Strapline here is high throughput workloads on Kubernetes. So first, a bit of an intro. So my name's Poole. I work for G Research. We're a fintech company based in London. We build and run a large distributed research platform for our teams of quantitative researchers, basically looking for patterns in large, real-world, noisy data sets, market data, financial data sets. And a bit of backstory for us, we're about 20 years old. We've grown quite a lot in that time, and we're currently migrating a large amount of our batch compute workloads from HT Condor on Windows through to Kubernetes on Linux. So around the beginning of the millennium, anyone working in fintech, you'd typically be working with .NET Framework and Windows because that's just the way things were. Over time, we've migrated quite a lot to Linux as machine learning has basically emerged and become a thing. Linux is the sort of de facto place to be doing all that kind of stuff, so it makes sense. And in the meantime, containerization and Kubernetes has emerged as a de facto orchestration platform for containers. So that was our target. So Armada itself, what is it? So the best way to think about it is probably an open source job queuing system for high throughput workloads. So most of our compute is dedicated towards running run to completion batch jobs, a large amount of on-prem compute. We use private cloud, so we use any public cloud. We kind of decided early on that we wanted to go big on Kubernetes and really invest in using Kubernetes as a common substrate for all of our compute. So we wanted to add the features that we needed to support all of our batch compute workloads onto Kubernetes, on top of Kubernetes, so and then use as much of Kubernetes capabilities as possible rather than replacing them. So I guess the key things that we were getting from Condor that we didn't get straight away from Kubernetes were things like fair share over time, supporting queuing large amounts of jobs, being able to basically ask for much more compute than there is physically available, and also having some kind of user interface and rich metrics so we could understand what's going on with the platform. The architecture of Armada is this diagram. So all of the blue boxes are Kubernetes clusters. So at the top level, the thing that users actually interact with is the component we call the server, Armada server. This has an API, gRPC API that people talk to. And behind the scenes, it has databases for events and jobs. But this is the thing that basically users talk to and say, hey, please run this job, where a job is I'll get to it in a moment, but it's basically a Kubernetes pod spec or a collection of those. And typically it's a researcher saying, please run this experiment, use this image with these arguments, take this input data, and maybe run 1,000 of those or even 1 million of those, for example. And then underneath, we have multiple Kubernetes clusters where the actual work is done. So these clusters we call executor clusters. That has a component deployed called the Armada executor. That thing has sort of free reign over the cluster and is responsible for looking at its local Kubernetes API, saying how much resource is available, this much CPU, this much RAM, maybe this many GPUs, talking back to the server component saying, hey, I've got capacity for this amount of jobs, what have you got? Leasing a job and then actually running it locally and managing the life cycle of the workload. And practically what that means is running some pods and basically keeping track of those. And then the key thing of the architecture here as well is we have multiple of these, so we can scale out horizontally quite easily, all leasing back to the single server up top. Core concepts that we have that sort of important to understand within the system are relatively familiar to anyone working at HTC background or HPC. So we have a queue. I've probably got these in the wrong order actually. Job's probably most the sort of top level thing. Job is the unit of work to be run. So that is the specification of that thing. Let's say it's a Python image that calculates pi or something. That would be the job saying, run this image, use these arguments, go. In Armada land, that's really just described as a Kubernetes pod spec. It's slightly decorated with some extra Armada stuff, but it's basically a Kubernetes pod spec. Then we have a queue. So within the system, we have the concepts of queues. The queue is the thing that the user interacts with. So a user will submit jobs to a queue and they get queued until they can be run. If the clusters are empty, they'll be run immediately. If they're not, they get queued. And the queue is a thing which represents really a user or a project or a team or something like that. And it's used to maintain fair share over time, and it has a priority factor. We have job sets, so they're really just a convenient way of talking about multiple jobs at the same time that are related in some way. So you can talk to the API and observe the progress of all the jobs in a set at one time. And then priority is an important concept as well. So queues have priorities relative to each other. So user A may have higher priority than user B within the system, but then even within a queue, there's job priorities. So jobs themselves have priority. So user A may have some jobs which are higher priority than some of his other jobs, and they will get scheduled first. I'll share the PDF of this presentation afterwards. There's links all the way through it, so you can click these and it'll take you through to our documentation if you want to find out a little bit more or get some more detail. So here I've got just some YAML, which is a sort of full example job spec for a job. So the stuff you see at the top is the sort of Armada specific stuff. So you see the queue, job set ID, maybe the priority, namespace, and some other labels that you can apply that Armada will apply to the jobs. And then underneath this, so you can see here we can submit many jobs. So this is a YAML list. So this just contains one job with one pod, but this job can contain multiple pods. And then the pod specs here are literally Kubernetes pod specs. So we haven't encoded this into our schema or anything. It's just literally anything that can be expressed as a Kubernetes pod spec can be placed here, and we just pass it through onto Kubernetes. We have a command line interface. So typically users interacting with Armada would use our CLI. So it's similar to kubectl in a sense. It's a convenient wrapper around our gRPC API. It's just a Go binary, self-contained. You just run it locally, and you can run commands such as submit. So you could submit a YAML file containing jobs like that one we just saw, and then you can run commands such as watch with a job set, and then you get this kind of feedback. So this is typically what a human would use when they're interacting with Armada. If you had other software that was interacting with it, it could invoke this, or it could just use the API directly, which is probably a bit more sensible. The API itself supports Kerberos authentication or OIDC as well, depending on your environment. We now have a UI. So this is something which we've created relatively recently, and we're trying to hopefully invest in quite a lot this year. We called it Lookout. It's a relatively basic UI now. It uses React, web-based, and allows you to view, just provides a view over queues and job sets, so you can kind of get a feel for the status of the system and what's running. It also allows you to view job logs, so you can click through and watch the logs of a job, which invokes Kubernetes logging underneath, and has some, at the moment, quite basic statistics for job runtimes, things like the longest running job and the oldest queued job, and on some other views, some sort of box and whisker diagrams show you sort of spread of how things have run over time. But yeah, there's going to be more to follow on that. I've got some notes here on scale and resiliency and why we design things in a certain way. So a lot of this is to do with why we went for the whole let's go multi-cluster from the beginning. We were kind of aware that we've got a large amount of compute and we want to be able to scale and not really be constrained by our software. We know that Kubernetes doesn't scale indefinitely. So I think the limit as of now is still at 5,000 nodes for a single cluster, although anecdotally it's quite hard to get it past a couple of thousand. You have to start really, bending over backwards and contorting yourself to make that work. And also a single cluster can fail. It's still a failure domain, even though it is a cluster. If you release a bad config change or some other unexpected thing, you can lose a cluster. So we didn't want losing at least one of those executive clusters to knock out the whole system. And then finally as well, we wanted to allow for different clusters to have different qualities. So they could even be in different places. One could be in one data center, one could be in another. Maybe one could even be in public cloud, one could be in private cloud. We didn't want to have to constrain ourselves to a single one. And then on the high throughput side of things, so really matching what we currently get out of Condor and maybe other systems, we wanted to make sure we could support handling a very large number of queued jobs, so order of millions. We wanted to make sure we could enforce fair share over time between queues, and we wanted to ensure we had a low latency between jobs submission and job start, excluding obviously queuing time, and ultimately just being able to make the best use of our hardware. So we've got a lot of hardware on-prem. We want to make sure we're sort of thrashing it as much as possible. We want to make sure that if there's a queue of workloads, and we don't really want to have hardware sitting idle because it's basically a waste. And then some notes on Kubernetes scaling itself. So we typically now run clusters up to about 1,000 nodes because of those previous considerations I mentioned. Even that has some scaling challenges, so we've had to do some work to make that sort of easy. So first, the build automation, so being able to build at that scale in the first place, we use Terraform, so we had to do some fun games there to make Terraform work properly with that many resources. And then we've had some work around scaling our CNI, so we use Calico for the networking within our clusters. That had to have some adaptations to work at that scale, and then some other bits and pieces around Prometheus and monitoring. One thing that was particularly interesting, we pay a lot of close attention to, is any system components that run as daemon sets. So anything that runs on a single node, every single node. Obviously, we want to make sure that we understand how much resource those are using, because if we can save a core on every node, then that's a large net saving and allows more room for our jobs to run. I put a link to a couple of blogs here. So OpenAI have done great work scaling Kubernetes to some quite extreme levels. So they've gone to, a couple of years ago, went to 2,500 nodes, and recently they've done 7,500, which is pretty insane. I don't think we'll ever go to that kind of level, but it's good to know that people are out there doing these sorts of things. But yeah, we will probably stick to around sort of order of 1,000 and just scale horizontally, but just adding more clusters. I've got a demo here. So this is a video we made. It's quite an old video, actually. So it doesn't show Lookout, it just shows some Grafana dashboards, but it kind of gives you an idea of how the thing works. So I'll just open this in a new tab, and it's 15 minutes, so I'm not going to play all of it, but I'm going to skip forward to the action. I'll talk you through some key bits. So what we have here is an Armada setup in AWS. This is a Grafana dashboard, and it's just using Prometheus metrics, which are exposed by the system. And along the top here, we have our graph of queued jobs. So this shows you the jobs that are currently queued in the system. And then underneath, we have 5 columns where we have 5 executor clusters. I think all of them had 99 nodes, something like that at the time. And it's relatively expensive, I think, to run that in AWS. So we had it all scaled down and then turned it all on just before this video. The green lines you can see along the top of the 5 charts along the bottom there is available CPU. And then you can see the color-coded jobs that are being run, adding up to sort of almost all the total CPU. So I'm scrolling down now, so wait for that to go back up. The yellow line is the overall total used CPU. So we're trying to get that quite close to the sort of available, basically. What's happening here is we've got 5 different users, all submitted jobs, all at the same time. Not a very real life situation, but you get the idea. All being worked through fairly equally because they've all got the same priority. And then this 6th user, the blue one that's come along at the end, Fred in this case, has a higher priority than the others. So those jobs are being consumed faster. And if you look down on the graphs underneath, you'll notice that the blue segment is appearing and sort of pushing the others out in a sense. These are all quite short running jobs. So I think they're running for some small number of, approximately 60 seconds. Sorry.
So question. So you're showing the aggregate CPU for all the nodes in the Kubernetes cluster, right? Here.
That's what that yellow line is. Yeah, that's the aggregate.
Okay, got it. And then, but you're not showing how many nodes you have, right? So
no, I think, yeah, there was another view. I can't change it because it's a video, unfortunately. But if we were to scroll down, we would see there's a row for CPU, we've got a row for memory, we've got a row for nodes, and it pods even as well. So you'll be able to see pods. You can see, in fact, probably roughly guess the total jobs queued was 20,000. So each of those would be a pod, and we've already gone down to about, I don't know, 15,000, 12,000 or something. So in the time between, 5 minutes or so, about 5,000 jobs have been run. So yeah, they're relatively short. And then I think what we'll see is this large blue wedge will finish up, and then all the other users will start to get their priority back. Mm-hmm. But yeah, this goes on for a little longer, but you can kind of see some other charts here. We've got a constant, the priority there going up. So this is a slightly confusing concept, I suppose. I think the priority numbering is sort of that 0 is the highest priority, and the higher the number goes, the less priority you get. I think we actually copied that from Condor.
Another question is, so as the jobs are running, are the pods scaling up and down, or the pods remain the same, but you're actually changing the CPU requests?
The pods are, yeah, good question. We don't change the request to the CPU or the pods or anything like that. It's literally what is specified at submission time. So within the spec, people specify the resources they want or need, and then that's taken into account when we're running jobs. We just use the Kubernetes scheduler there.
Okay, so you specify the limits, right? And then the requests actually change or something? Is that?
I think we enforce that people specify the request for CPU, and I think the limit for memory, because I think that's how scheduling works in Kubernetes.
Okay.
But yeah, that's right. I think if you don't specify at all, then it depends how you configure Kubernetes, but we have some default limit ranges, which are some quite small values. So I think typically researchers here will always ask for integer CPU cores, but yeah, typically one or many, and same for GPU. In this case, I think, in fact, we've just flipped to it now. You can see this is the IDE where the jobs were submitted from. They're now looking at the watch command to see how things are running. I can actually see there's a tiny slither on the IDE up there where we can see they're asking for millicores, so 0.2 CPU.
Got it.
But yeah, I think from memory, these jobs are actually just sleeping. Oh no, that's not true, because they were using CPU. I think they were doing some kind of DD command or something to try and sort of burn the CPU as much as possible.
Can you express things like performance considerations or latency to guide where you are going to dispatch or queue things?
How do you mean? Sorry, expand on that.
Or depending on which cloud instance or platforms you're planning to schedule particular executions, do you take into account performance or latency for accessing these?
Oh, I see what you mean. Not by default, but that can be opted into. So I guess it depends on your environment, but we basically just use Kubernetes concepts to allow scheduling. So if you can have things like node selectors or taints and tolerations even. So if you had a particular requirement for, I don't know, data locality or something like that, or some particular hardware, then you could express that in your pod specification, and then it will get taken into account when scheduling. If you don't, then you'll just get scheduled wherever.
Okay.
That's the sort of design. Right, I'll just stop the video. So I've just got a few more slides. Cool. Okay, so I'll just talk briefly about the roadmap, where we're going. So we've got a decent idea of what we want to achieve over the next year. We've kind of broken it up into these kinds of themes. So we want to kind of invest quite heavily in the observability side of things. We rely quite a lot on Grafana at the moment internally, which is fine, but we want to try and build as much of this kind of observability and understanding into our Lookout UI as possible. So our users who aren't necessarily Kubernetes admins or even particularly au fait with Grafana and Prometheus, to be able to just click around and have views to answer those sort of really common questions like, why isn't my job running yet? Why is my job performing or not performing properly? You know, how much fair share am I getting on the system? How much resources are available? All of that kind of stuff. We want to build that into the UI and make it really intuitive and easy for people to use. We're going to try and add some support for maybe some slightly smarter scheduling and distributed jobs specifically. So we'd like to be able to sort of run bigger ML things where we maybe schedule the big gang scheduling kind of thing, you know, MPI kind of stuff, running multiple things at once that talk to each other. And we're trying to also really add to the open source offering around tooling. So a lot of the work we've done here, which we haven't yet open sourced, is around how to configure our clusters easily to be able to support this kind of workload, and also integrate with other open source tools like Kubeflow and Spark and other things that other researchers might be using, because we often get asked the question, how does this interact with Spark or Kubeflow? And we don't necessarily have a good answer for that at the moment. So getting some good sort of examples of that, I think, would be really beneficial. And I think this is a final slide, but I've just got a link here to our quick start. So it's quite easy to try it out if you want to get a feel for how it works and what it is. The quick start guide just guides you through a local installation, which is obviously not for use in anything like production, but just on your local machine. It will spin up a few clusters using kind Kubernetes in Docker, deploy the application there, and then let you submit some jobs and sort of get a feel for how it works and what's going on. At the end of it, you'll be presented with a Grafana dashboard like this, where you can see what's happening, and also the UI is deployed so you can access that as well. And that's it for my presentation. So yeah, thank you very much for listening. I'm Jamie, and I'm the Compute Platform Engineering Manager at GR, and a couple of links there to the GitHub for Armada and also the standard plug that we are hiring.